All right, so Taylor polynomials and Maclaurin polynomials can be used to approximate the value of a function at a specific point. We already saw that, right? When we were looking yesterday, we used it to approximate the value of cosine of 0.1, right? And we found that it was this value. And we also noticed that the value we were trying to approximate it at was very close to the center of our function. Okay. So let's go back to this. It says, for instance, to approximate the value of natural log of 1.1, you can use Taylor polynomials for natural log of x expanded about the center of 1. That makes sense because 1.1 and 1 are very close. Or you can use a Maclaurin polynomial as shown below. Okay. Now we know the Maclaurin polynomial, the center would be 0. So here are some things that we need to consider, right? We know that the c equals 0, that makes it Maclaurin, but we also know to estimate with the most accuracy the x value should be close to the center, and 1.1 is not very close. So using natural log x might not be a good choice. Also, if you try to use natural log x, it's going to be kind of hard because the first derivative is 1 over x, and we know in that middle column of construction, you need to plug in that center to your derivatives, and that's going to be an issue. Okay, so for those reasons, we are going to consider using a related function. Okay, and the related function we're going to use is natural log of 1 plus x with that center of 0. And the reason that we can use to approximate that is because if I use an x value of 0.1, that would make natural log of 1.1, and 0.1 is close to c equals 0. Okay, so that's kind of the game plan here. Okay, so I need to go ahead and set up my 3 columns so that I can actually construct this Maclaurin. Okay, I know I'm going to need to take 4 derivatives because it's asking for the 4th one. All right, so starting with my function, natural log of 1 plus x. Okay. My first derivative then is going to be 1 over 1 plus x, which is the same thing as 1 plus x to the negative 1. My second derivative is negative 1 plus x to the negative 2. For evaluating purposes, I might do a quick rewrite here, okay? But for derivative purposes, I'm probably going to keep it with negative exponents. Here, this would be 2 times 1 plus x to the negative 3, which is the same thing as 2 over 1 plus x cubed. And finally, my fourth derivative would be negative 6, 1 plus x to the negative 4th, or negative 6 over 1 plus x to the 4th. Okay, and now my job is just to plug in 0 for all these, and that's not so bad. If you plug in 0, you have natural log of 1, which is 0. Okay, if I plug in 0 here, I'm going to get 1. If I plug in 0 for x for the second derivative, I'm going to get negative 1. If I plug in 0 for the third derivative, I'm going to get 2. And if I plug in 0 for the fourth derivative, I'm going to get negative 6. These are not my coefficients though, right? I still have to go over here. All right, I know if I do 0 divided by 0 factorial, it's still going to be 0. 1 divided by 1 factorial is 1. Then I'm going to have negative 1 over 2 factorial, 2 over 3 factorial, and negative 6 over 4 factorial. These are all my coefficients, and they're going to go with my powers of x, right? If I want to, I could simplify this right here because I'm not looking for a pattern. It might make sense to go ahead and simplify these. Again, you are not required to. It might be good to practice every once in a while just in case for that multiple choice question that you feel comfortable simplifying these. So my fourth Maclaurin polynomial would be 0, which you don't have to write, 1 times x, negative 1/2 times x squared, 1/3 times x cubed, minus 1/4 times x to the 4th. Okay. All right, so this is my Maclaurin polynomial, right? And so if I want to use that to estimate natural log of 1.1, Okay, then that would be the same thing as natural log of 1 plus 0.1. So that's the same thing as approximately that fourth Maclaurin polynomial where x is being replaced with 0.1. Okay, and so all you're doing is typing that into your calculator. Okay, and if you do that, you should get approximately 0.0953083. If you just type natural log of 1.1 in your calculator, okay, you get 0.09531011798. And comparing those, these are really close, right? So that means that fourth Maclaurin polynomial was a pretty good estimation. Okay. All right, and real quick before we wrap up this particular video, so here's this table on the next slide shows you that if you had used a Maclaurin polynomial of degree 1, this would have been my estimation, right? And by the way, I'm comparing it to this, okay, which is actually natural log of 1.1. If I use the second degree, I'm definitely getting closer, right? If I use the third degree, even better. The fourth degree, even better. And so we can see as n increases, it actually approaches the actual value. So the more terms you use of that Maclaurin polynomial, the better the estimation will be, which I think makes sense. Okay, on the other hand, the table illustrates that as you move away from the actual center, the accuracy decreases. Okay, so if I look at this, right, if I move away from the center, that's what these x values are doing, right? When I'm at 0, they're all the same because I'm actually at the center, so that makes sense. As I move a little bit away at 0.1, I'm still at a pretty good estimation. As I move farther away, right, I'm comparing this with this. It's not awful, right, but it's starting to get further away. As I move even further, you can see that these two have a wider gap. And when you're here, then things are really getting wide. So 2 important points about the accuracy of Taylor and Maclaurin polynomials for use in approximation. So these are kind of the 2 things to keep in mind. The approximation is typically better for a higher degree Taylor or Maclaurin polynomial, right? So the larger the n value, the better off you are. And the approximation is usually better at x values close to c. Okay. So I want to have x values close to c rather than far away from c.